Cool. So yeah, my name is Layne Haber. I'm one of the co-founders at Connext, where I do research there, and I'm going to be talking about different bridge security models and their implications. So first, this has been touched on in the other talks, but bridge security is important because it lies at an infrastructure layer for these other chains that it's connecting. And if something goes wrong in a bridge, you could be left holding the bag, even if you've never interacted with a bridge. So this kind of details where some of that $2 billion that Chris mentioned earlier went into which hacks. This is not a complete registry, only that's happened in the last 365 days. But as you can see, these hacks are getting larger and larger because more and more funds are getting put into bridges. And I expect that soon we'll probably see, a $1 billion hack on a bridge, regrettably. But that just underscores their importance, a growing importance in the ecosystem. Another reason why bridge hacks are so malicious is, again, you could be the collateral damage, but that goes to this contagion risk. So lots of bridges work by, being able to back assets one-to-one. And this is for example, how all of the Polygon, the POS bridge, or the roll-up AMB bridges, or the Gnosis Omni chain bridge, they all custody funds and then allow you to use an adopted asset on their chain. The risk with bridges is if the bridge gets hacked, then those funds would no longer be backed one-to-one, and you could be left holding the bag. So, scary example, but if this were to happen to the Polygon POS bridge, now you can enter Polygon through just using your credit card, which means that you're exposed to this bridge risk, even if you've never used the bridge. So it can be something that you don't realize you're exposed to. So now I'm going to go into different types of security models. The first is a natively verified bridge, and this is where your domain's underlying validators are the ones who are verifying the transactions. So you can think like clients or, roll-up AMBs or the Polygon POS bridge, but the underlying domain validators are the ones who are validating the bridge itself. There's also externally verified transactions where the validator set is actually not part of the underlying domain validators, but it is now just a third-party set of validators who can be incentivized through a variety of different ways, but they're the ones who make sure that these transactions between the two domains net out. And then you have optimistically verified bridges. Optimistically verified bridges operate in a similar way to optimistic rollups. And by that specifically, I mean that there's a delay window where anybody can submit fraud. How fraud is proven is there is a Merkle tree of updates stored or messages stored on the origin domain, so where the message is sent from, and you can prove that some route is incorrect on the origin domain. Now, to disconnect other domains from processing that message, you would have to rely on a watcher to call disconnect on those domain. It is important to note that while the home can be only the origin chain can prove fraud, but the destination chains can be disconnected by a trustworthy watcher. So when we talk about bridge security, there's three main things or questions that we're talking about, and three different types of security. So there's economic security, which is basically asking the question, how much would it cost to corrupt your system? The implementation security, which is how difficult is it to implement, and how secure is the design outside of the implementation as well. And then you have environment security, which is how can your system handle underlying domains with low economic security. So what I mean by that is bridges are generally an oracle of information and state from one chain to another. You can have chains that are connected that don't have equal levels of economic security at the base layer. So for example, connecting Cardano to Ethereum, Cardano is probably easier to corrupt and censor than Ethereum is, but the bridge is basically what would allow malicious state on Cardano to be transferred and honored in Ethereum and kind of break that integrity on the higher security domain. Cool. So economic security, what's your price? How much does it cost to corrupt all of the validators in your system? So for natively verified bridges, you would have to corrupt the underlying domain validator. So you would have to 51% attack the underlying domain to be able to violate the economic security. externally verified systems, you actually just have to corrupt the bridge validator set. I referenced the Ronin hack here, even though they weren't bribed, but they did lose keys, which showed the implications of having a corrupted external validator set. And then for optimistic security, there's actually a few different bribes you can execute. One is for the entire watchers, so preventing any of the watchers that are online from disconnecting any transaction or proving any fraud would certainly be problematic. You can also censor the home chain, so that's where the disputes are initiated and fraud is proven. You can prevent the fraud from the prove fraud transaction from actually being submitted on the home chain or wherever the messages are sent from. And then there's the last one, last bribery opportunity where you could actually bribe the destination domain and censor that domain, so the validators there, so that the watchers, even if they are honest, can actually disconnect the domains. So in terms of ranking, the most secure for economic security is native. And this is because you're really going to want to maximize the diversity and permission and size of your validator set. And native domain or natively verified bridges do that in the best way. Optimistically verified bridges, the reason why they're second is because it can be difficult to know who all of the watchers are, and you would have to bribe all of them, because even one watcher who couldn't be bribed would be able to disconnect the chain and prove fraud. And then you have externally verified, where you just have to bribe the external validator set or even some majority of the external validator set. So the next one is implementation security. You have to keep it simple. This has been, this is a problem for any smart contract system. Software is hard, so try and keep your implementations as dumb as possible and keep them as extensible as possible. So some of this simplicity can come from the nature of the protocol itself, and some of the security for implementation would have to come from the team itself. So what do I mean by that? I mean, like, you have to have fast response times, like Chris highlighted. You have to have monitoring. You have to make sure that you go through audits. What's your test coverage look like? Like, basically a cohesive, secure development process is important. But there are also things that you can do to build in defenses against certain hacks. This is similar to what was mentioned with the pre-crime stuff, although we call them circuit breakers or rate limits. But basically the concept there is, if you have a transaction that was withdrawing 0.01% of the bridge supply in one transaction, that's probably fine. But if you have a transaction that says it would want to withdraw over 90% of all the funds locked in the bridge, well, maybe that one requires some additional verification. So natively verified bridges tend to depend really deeply on the consensus of the underlying domains, which means that you can't have the same implementation be used multiple times. So this becomes very difficult to implement. And then for externally verified systems, you can have the same set of logic because it's not intimately tied with the consensus of the domains that validates the transactions that happen. However, you're probably going to have some more complex off-chain coordination between all of the validator sets off-chain, or the validators who are securing that bridge off-chain. With optimistic bridges, you are able to port the same implementation to multiple different domains because it's not dependent deeply on the consensus. And additionally, you have kind of isolated agents who don't need to communicate with each other. So you have the updater who is responsible for, similar to a sequencer and a rollup, they put their stake on the line, they're responsible for ensuring the integrity of the messages. And then you have a series of isolated watchers who are there to prove fraud and potentially react to it. So in terms of which model is the most secure with respect to implementation security, optimistic is the best, and followed by external, because you can easily port both of those models to different underlying domains. And the third is natively verified bridges, because you can't easily port the same implementation to new domains. So when you're trying to add a new domain, you'd have to come up with a whole new implementation, which doesn't necessarily have the same security because it hasn't been battle tested in the same way, but rides off a similar brand. The third one is environment security. And what I mean by environment security is like, how can you prevent 51% attacks on the underlying domain? This is all about ensuring that you maintain the high integrity of environments that have a really high economic security. So in the Cardano to Ethereum example that I gave, it would be ensuring that Ethereum did not react properly to the Cardano fraud from 51% attacking that domain. So with natively verified bridges, this doesn't happen it doesn't defend against this very easily, because really the only way you can defend against this is by taking advantage of asynchronous models and making sure that somebody off-chain is validating that the two steps are, that there is no underlying 51% attack. And then you have, for externally verified systems, it is very easy to add this type of delay in checking, but it's not necessarily required for the protocol. So it's not correct by construction, but that added degree of security can easily be added. And then for optimistic systems, they have a delay embedded in the protocol, which means that these types of risks types of detection measures can be easily added without having to, change anything fundamental, and the delay to react to that is already embedded. So who wins here? You see optimistic is probably the most secure for environmental security, followed by external, because again, you can easily add those checks in, but it's not required, or add in the delay in those checks. And then the third is native, because there is no way to check that if it's depending on consensus, and consensus is where the problem exists. So the final rankings here, economic natively verified bridges are the most secure. For implementation, optimistically verified bridges are the most secure. And for environment security, again, optimistic takes the cake. But keep in mind that there is some nuance here, and you're going to have to pay attention to kind of the details for the implementation of any bridge that claims it's optimistic, and any bridge that claims it's native, and any bridge that says it's externally verified. So yeah, happy to go to questions. We're hiring as well. But let's just jump to the panel.